good.
All right, so it's Cool Guy Sam again.
What the heck?
Tagon. Today we're going to be doing a video on what you should do when you multiply complex numbers. What I'm trying to get at is the fact that's taught many times in complex analysis courses as well as just in algebra classes if it gets that far, which is that when you multiply two complex numbers together, you end up multiplying their sizes and adding their angles. And today we're gonna sort of explore what that means, and we're gonna be doing it on the trail again. So we're back to trail math, of course. So what do I mean by complex number? Well, we have ourselves the complex plane, and a complex number is any point in this plane where we ask how far in the real direction is it? We'll call that A. How far in the imaginary direction is it? We'll call that distance B, but since it's up in the imaginary direction, we're gonna multiply by that ever lovely constant I, which is the square root of -1. And what we say is that this point in the plane is A plus BI. So this point is its own number. Just like we have real numbers on the number line, we now have this extra dimension to allow an entire plane of numbers. All the numbers you're familiar with, the real numbers are right there on the real number line. All of the real numbers times I are right there, and then every other point in the plane is a nice combination of those two. So if we say this is the number Z for short, or Z if you're more cultured and anywhere else but here, then we want to know, okay, let's say I have another complex number. We'll just pick this point down there, and we'll say that's W equals C plus DI, right? So C is the real part here, and D is the imaginary part. So this will be C, and that will be D times I. What happens when we multiply these two complex numbers together? Adding them is very easy, but we're going to try and explore what happens when we multiply them. Most importantly, without having to refer to Euler's formula or anything to do with the angles in like the trigonometric sense that you learn about when you sort of generalize complex numbers to, or at least another way of representing them. We're going to stick with the rectangular form, and all we're going to need is the inverse tangent function, and we'll be great. So let's move on. Oh, gosh, I am really tired. So come over here and let's learn more about multiplying complex numbers. Hi, guys. Let's learn a little bit about complex numbers. So we have a couple complex numbers in the complex plane here, and when we add complex numbers together, it's not too difficult to see that we'd want to combine their vertical distances, which is to say that we're adding the imaginary parts. So BI and DI will add together to make B plus D times I, which again is the square root of -1, and we'll add the horizontal distances together. So we're going to combine A and C. We're going to add A and C together. So you're basically adding like terms. That's how we add complex numbers. Multiplying them is a little bit more difficult, but it's nothing you haven't learned before in algebra. It just involves foiling out the product. So we're going to multiply the first things, the outside things, the inside things, and the last things. Foil, F-O-I-L. I'm going to speed through this part.
You end up with?
And what you end up with is an expression that looks like this. The real part becomes A times C minus B times D, because the I times I is I squared. That's -1, so you get a minus sign. And the imaginary part is A times D plus B times C. That's how we got that there, times I. Now, the problem with doing this in rectangular form, where rectangular form is what we have here, right? A horizontal distance and a vertical distance. It sort of makes the two sides of a rectangle. That's very easy for addition because it's a very obvious and clear answer as to what happens. The horizontal distances add together and the vertical distances add together. The problem with doing multiplication in rectangular form, though, stop scratching yourself, Gus, is that this doesn't tell us anything really like immediately obvious about where the resulting point is, right? Where does the product end up, right? How does that work? And you'll learn, especially when you encounter what we call Euler's formula. You encounter this expression right here. This allows you to very, very quickly express things in polar form, and you see the result that when you multiply complex numbers together, what you do is you multiply their sizes and add their angles. But that's not really something we can see in this expression here, and so what we're going to do is we're going to prove that that's still true using rectangular form and ignoring polar form altogether. So as cool as Euler's formula is, and as beautiful as it is, and as useful as it is, we're not going to be utilizing that today. So in the next spot, we're going to discuss what the modulus or size of a complex number is, as well as the argument or angle. I'll see you there. Okay, I knew we'd have to cross this bridge when we came to it. So we're going to have to review now, what do modulus and argument mean in the context of complex numbers? Well, we've already learned about the rectangular way of interpreting complex numbers, which is the horizontal, wow, that was terrible. The horizontal component, the a value, and the vertical component of a complex number, the rectangular form, right? But another way to look at it and to interpret complex numbers is instead to ask, how far away from the origin is the number, and what angle does that sort of vector to the number make with the positive real axis? And so the modulus of our complex number that we'll call z, or z again, the modulus of z, which is just a fancy word for absolute value, is just how far away that number is from the origin. So r, whatever this length is the modulus. So that's often noted like this. So you use the absolute value symbol like you would learn in regular algebra. And how can we calculate the length of this line segment? Well, it's very easy, because this here we have is a right triangle. It's got a height of b, and it's got a horizontal component of a. And so we can find the hypotenuse of that right triangle by simply using the Pythagorean theorem. So we know that the modulus of any complex number, or the size of it, how far away from zero it is simply the square root of the sum of the squares of the rectangular components. So it's the square root of a squared plus b squared. That is the size of the complex number, how far away from the origin it is. So we've figured out modulus, so I'm going to replace that with an exclamation mark, because we're all done with that. So that is the modulus of a complex number. Next, we want to talk about the argument. The argument is just another word for the angle that it forms with the positive real axis. And we note that with a function that we literally call arg. So arg of z is simply this angle here. This is theta. But how can we express theta, and by the way, this is r from before, right? That length r. How can we express theta in terms of a and b? Well, we just need to use a little bit of trigonometry. So you may recall from learning about trigonometry that you can define a function called the tangent function, and that tangent function is you plug in the angle inside of your right triangle and you get the quotient of the opposite side and the adjacent side. So the tangent of our angle theta is going to be b over a. But we don't want the tangent of the angle, we just want the angle. So we're going to take the inverse tangent of both sides, and we see that theta is the inverse tangent of b over a. So now we've got these completely well defined. And what we want to do, or what the goal of this video is to show, that when you multiply two complex numbers together, what happens is that you end up, the complex number you get has a modulus that is the product of the moduli of the two numbers you multiplied, and has an argument that is the sum of the two arguments of the numbers that you multiplied. So that's... Howdy, folks. So a little reminder before we keep going is something called the tangent sum formula. So we have the tangent of the sum of two angles, we'll call them alpha and beta, and you may recall from algebra class or trigonometry class or whatever, that if you have the tangent of two angles added together, that can be expressed as, well the angles are alpha and beta, so the tangent of alpha plus beta is the same as the tangent of alpha plus the tangent of beta, all divided by 1 minus tan alpha times tan beta. And we're going to utilize this to prove the fact about the sums of the arguments of the two complex numbers that we're going to multiply. But first we need to do a little bit of a replacement in here and a little bit of a change to see what I mean. So first what we're going to do is we're going to replace every angle alpha with the inverse tangent of some number a. And we're going to replace every angle beta with the inverse tangent of some number b. So if we take this inverse tangent of a and plug it in for alpha, we're going to have the tangent of the inverse tangent of a. Those tangents and inverse tangents are just going to cancel. They're going to go away. And so what we're going to have here is just a plus b, because these tangents will cancel with these inverse tangents. So the numerator will be a plus b, and the denominator will just be 1 minus, well, we're plugging in inverse tan of a in there and inverse tan of b in there. So the tangent of the inverse tangent of a is just a. and the tangent of the inverse tangent of b is just b. So plugging in these inverse tangents for the angles alpha and beta drastically simplifies our expression, and plugging them into there will sort of make this left-hand side a little bit more complicated. But before we plug them in for alpha and beta there, what we're going to do is we're going to take the inverse tangent of both sides of this expression. So this entire fraction is going to have the inverse tangent function applied to it. So a plus b over 1 minus a times b is just some number, right? And we're taking the inverse tangent of that. And since we're taking the inverse tangent of the left-hand side as well, we're just going to be left with alpha plus beta. But what is alpha plus beta? Alpha plus beta is this plus this. So this expression is equal to the inverse tangent of A plus the inverse tangent of B. So what have we just done? We've just taken the tangent angle sum formula, which is here, and rearranged it into a way of re-expressing the sum of two inverse tangents. So two inverse tangents added together can be rewritten as the inverse tangent of a single number. And this is the fact that we're going to be using to prove the argument fact that I stated earlier. So on to the next spot. Okay, so let's recall what the goal of this video is. The goal is to prove, without using Euler's formula and just the rectangular form of complex numbers, that when we multiply two complex numbers together, we end up multiplying their moduli and adding their arguments. In other words, we're multiplying their sizes and adding their angles. That's all that means. So quick review, we've got z is a complex number a plus bi, and w is a complex number c plus di. We saw before that when we multiply w and z, we end up with this rectangular form for our complex number. The real part is ac minus bd, and the imaginary part is ad plus bc. And what we want to show is that the modulus of the product of those two numbers is equal to the product of the moduli of the individual numbers. In other words, whatever complex number we end up getting, the distance of that complex number to 0 is going to be, that distance is going to be the product of this distance and the product of that with that distance there. So that's what we want to show, where the moduli of z is the square root of a squared plus b squared. That's this distance right there through the Pythagorean theorem. And the modulus of w is the square root of c squared plus d squared, and that's that distance right there. So that's our goal, and that's what we're going to show now. So how we're going to prove this is we're first going to start with the modulus of our product and show that it turns out that it's just the product of the individual moduluses, moduli. So what is the modulus of this number, of this complex number? Well, the modulus as we defined it is just the square root of the sum of the squares of the real and imaginary parts. So the modulus of z times w is going to be the square root of the real part ac minus bd all squared plus the imaginary part ad plus bc all squared. And what we want to show is that this is just the product of those individual square roots that we had before. So we can do that first by foiling out all of the stuff in here. So this is going to be equal to a very sped up part of the video. Okay, so when we FOIL out all the stuff under the square root, we end up with a squared c squared minus 2abcd plus b squared d squared plus a squared d squared plus 2abcd plus b squared c squared. So a big, mishmash of letters and stuff, but you're going to see that it's all going to cancel very, very nicely. All we did was, FOIL out some binomials like you will have learned in algebra class. You'll notice we have a minus 2abcd and a positive 2abcd. These are, of course, going to cancel each other under the square root, and we're just left with the sum of these four squares here. So next step, what I've done here is I've just rearranged the remaining four terms to be a squared c squared plus a squared d squared plus b squared c squared plus b squared d squared. And what we can do is we can factor out a common factor of a squared from these two terms, and we can factor out a common factor of b squared from these two terms. And now you'll notice, after factoring out a squared from here and b squared from here, we now have a common factor of c squared plus d squared in both of these terms, so we can factor that out. And even though it's a little bit slanted, I think you can now see that after we factor out that c squared plus b squared, we now have under the square root the product of a squared plus b squared and c squared plus d squared. Now, you may all remember that the square root is nothing but the power of 1/2, and powers always distribute onto products. So we can say that the square root of this product is equal to the product of the square roots, and so I can rewrite this as simply the square root of a squared plus b squared times the square root of c squared plus d squared, which I think you'll agree is the modulus of z times the modulus of w, which is exactly what we wanted to show, that the modulus of the product of two complex numbers is equal to the product of the individual moduli. So that is the first part of our proof done. Next, we want to show that you simply add the angles. Let's go to the top of the mountain. Step of our video today. So previously we just proved that the size of the product of two complex numbers is equal to the size, or the product of the individual sizes, usually called the modulus. And now we're going to prove that the angle of the complex number that you get with the positive real axis is just the sum of the angles that you multiplied, the sum of the angles of the complex numbers that you multiplied. And this, the phrase we use is argument as opposed to angle. And recall previously we defined the argument of a complex number z to be the inverse tangent of the imaginary part divided by the real part. That's basically just using the tangent function and right triangles. Similarly, the argument of this complex number w will be the inverse tangent of d divided by c. And we want to show that the argument of the product of the two complex numbers is equal to the sum of the arguments of the two complex numbers that we multiplied together. Since z times w is this product that we got previously, ac minus bd plus I times ad plus bc, it's clear from our definition of the argument that the argument of this product is going to be the inverse tangent of this number, the imaginary part, divided by this number, the real part. And what we'd like to do is reconstruct this inner stuff in here so that it looks like the sum of these two inverse tangents based on the thing that we just derived a couple parts ago. So let's do that right now. So from the formula that we derived previously, we see that the sum of the two arguments, which would be the inverse tangent of b over a plus the inverse tangent of d over c, can be combined into a single inverse tangent expression, again based on what we derived previously. And we saw that that should become the inverse tangent of this term plus that term, so the sum of the two fractions in the numerator, divided by 1 minus the product of those two fractions. So now what we're going to do is we're going to multiply the top and bottom of this fraction by a times c. That way we clear all of the denominators. So let me just write that out real quick. Okay, I've multiplied everything in the numerator and everything in the denominator by a times c. And now we're going to see some pretty good cancellation. We're going to see a cancel with a, so we're just left with b times c. We're going to see the c cancel with c, so we're just going to be left with a times d. A times c is all good, and here we're going to see a cancel with a and c cancel with c, and we're going to be left with the inverse tangent of bc plus ad divided by ac minus bd, which, other than just flipping that sum in the numerator, is precisely the expression that we derived for the argument of the product of our two complex numbers, a plus bi and c plus di. So this is precisely the sum this is precisely the argument of the product of those two complex numbers, which means we've finally shown that the argument of the product of two complex numbers is equal to the sum of the arguments of the two complex numbers. So not only have we shown that the sizes multiply, but we've shown that the angles add, and there was no need to invoke Euler's formula whatsoever, but of course Euler's formula is still very, very cool. So now on the screen you should see my proofs of that fact. So go check those out, and don't you dare watch anybody else's. Thanks.